Okay, so in this example we're going to consider a system often referred to as Newton's cradle, which is a system of n pendulums which are hanging from a common support. And in this case we're told that the particle for pendulum 1 has given an initial horizontal velocity v0, after which it subsequently strikes particle 2, which then sequentially strikes particle 3, which sequentially strikes particle 4, etc. And given the coefficient of restitution of all the impacts e, as well as the initial velocity v0, what I'd like to find in this example is the speed of particle n immediately after the final impact, and also the maximum height h reached by the particle n. Now it turns out that this problem can be either very easy or very hard, and for the context of this class we're going to focus on the easy one. The easy one's going to be where we assume that each of the impacts occurs sequentially, that is 1 strikes 2, which then strikes 3, which then strikes 4, and on down the line. We're not going to allow for multi-ball impacts or simultaneously impacts to occur. If one does this, it's relatively easy to figure out how to solve this problem. In this case, I'm going to limit myself to looking at 2 particles, and I'm going to sketch a free body diagram. In this case, we have some tension, which I'll call T1, as well as a tension T2, and we'll have 2 weight forces, which because the mass of the balls are equal, will both be mg. The important thing to note here is that we have conservation of linear momentum in what I'll call the x direction, using a conventional xy coordinate system, because there's no forces acting in the x direction. So if I look at conservation of linear momentum in the x direction, what I'm going to have here is that m times v0 has to equal m times what I'll call v1 prime. I'll use a prime to designate a post-impact velocity in this problem, plus m times v2 prime. We'll note that the masses cancel here, and so I end up with the result that says that v0 is equal to v1 prime plus v2 prime. Again, prime denoting post-impact velocities. Now, this obviously gives me one equation with 2 unknowns, and so the other thing I'm going to use here is the impact rule. If I use the impact rule, it says the coefficient of restitution is given by the difference in post-impact velocities in the n, which will be v2 prime minus v1 prime, divided by the pre-impact velocities, which will be v1 minus v2. If I go ahead and substitute in the numerical values I'm given here, this gives me that E is equal to v2 prime minus v1 prime divided by the initial speed v0. I can take this information and solve for v1 prime, and so if I do that, what I'm going to have here is that v1 prime is going to equal E times v0. Actually, let me rewrite this a different way. I'm going to rewrite this as v2 prime minus E times v0. Why do I want to write it that way? Because I want to then take this result and I want to plug it back into my original equation I had here up above. And so if I do that, what I'm going to end up with now is that v0 is equal to v1 prime, which is v2 prime minus E v0 plus v2 prime. If I rearrange this equation a little bit, what I'm going to have is that v2 prime is going to equal quantity 1 plus E divided by 2 times v0. Now this is important. What this gives me is the post-impact velocity of the next pendulum in the array given a previous speed on the previous element. Well, another way of saying this is that the speed post-impact of the next pendulum in line is going to decrease by an amount given by 1 plus E divided by 2. Note that if we have a perfectly elastic impact where E is equal to 1, the speed of the next pendulum post-impact will be identical to v0. If E is less than 1, that is, there is some elasticity in that impact, that number is going to be reduced. What does that mean? Well, what this means is that the velocity of particle n post-impact will be given by the initial speed v0 times the reduction factor, which is going to be 1 plus E divided by 2, times the number of impacts, which in this case will be n minus 1. If you had 2 impacts, or 2 pendulum system, as in the case we just looked at, you would note that this reduces to the same expression we previously had. Now why is that important? Well, once we have that information, we can apply work energy to determine the maximum height obtained by the particle post-impact. How do we do that? Well, what we can say is that let's just go ahead and use the notation here, Vn plus Vn plus the work done in moving from the nth state to the nth plus 1 state, non-conservative, is going to equal what I'll call T final plus V final. Actually, I should probably make this n to the final state. And so we know the kinetic energy of the nth particle post-impact is going to be, in this case, 1/2 times the mass times its velocity squared, which is going to give me V0 times quantity 1 plus e over 2 to the n minus 1 power, all squared. Vn is going to be a function of where we put our datum, so let's go ahead and choose our datum to be up at the top, at the anchor point of that nth particle. So let's put it right here. I'll make my trigonometry a little bit easier here in a minute, so I'm going to have this is equal to minus m times g times the length that's hanging down L. There's no non-conservative work done post the final impact, so U here will be 0. The kinetic energy at the maximum angle of deflection, that is TF, is going to equal 0 because we're at the maximum angle of excursion. And VF in this case is going to be given by minus mg times L times the cosine of that final angle, which I'll call theta sub n. We can then take this information, namely these 5 expressions, and we can plug them back into the work energy equation here, and from that information you can determine theta is a function of n. Now surprisingly, what you're going to find is that as n increases, that maximum angle is going to decrease, and it's going to decrease in a way that not only is a function of e, but is a function of n. Alright, I think that's a good place to wrap up here today. I'll simply wish you the best of luck. Think about that Newton's cradle the next time you see one. Take care, everybody.